All right, so let's return to the styrene example now. So two styrene units by themselves do not react. Okay, so if you think about alkenes, how alkenes always react, alkenes have electrons and they're looking for somebody that wants them. So both of these things are nucleophiles or are looking for some electrons. So polymerization reactions always need some kind of an initiator to get them started. And for a large number of polymerization reactions, the initiator is some kind of a radical. So we want something that's going to form a radical. So that takes us back to our radicals chapter, and one good example are peroxides. And so this is t-butyl hydroperoxide. So if I take t-butyl hydroperoxide with either H nu or heat, either one, that will separate into the radical. So we got one electron breaks here, one electron goes there, and that bond. Remember, oxygen-oxygen bonds are quite weak, and so they're easy to break. Now we have our radical initiator. So now I can take that and react that with one molecule of the styrene. So why don't you pause now and try and see if you can draw this mechanism if you remember back to the radicals chapter. If you really don't remember, then you can go ahead and watch and just be refreshed. But if you can try and see if you can remember how this might work. As you're thinking about it, you might want to think about which will be the most stable radical that's formed when, if we form a radical here. Are we going to get the radical on the end, or are we going to get the radical that's in the benzylic position? All right, so this radical comes over, one electron from the pi bond comes over, one electron from the pi bond goes to a carbon, and we form our initiated material. So I now have a radical there, and I have my R group, or my radical initiator, here on the end. All right, so now I've got this radical that can go and react with another molecule of styrene to keep forming my polymer. So let's look at the two possibilities again and talk about why we get the material that we do. So our choices are either I can put my radical here on the end and my T-butoxy group here in the benzylic position, or I can put my T-butoxy at the end and the radical in the benzylic position. So why is it that the radical is preferred here in the benzylic position? Well, it's one of our areas, of course, and it's resonance, because this radical can then be transferred into the ring, and I can put it at each of the ortho and para positions, and that radical won't be isolated in one place. Instead, it's spread all across the ring. If I have the radical here, there's nowhere for it to go to delocalize. So this radical is much more stable than this one, which is why that's the one that's going to form. All right, so that was our initiation step, and this is now our radical chain reaction step, which is going to be repeated over and over again. One electron is going to come from my radical, one electron will come from my alkene, one electron will go again to the benzylic position, always to that same spot because that's the more stable radical, and now I'll form a dimer, or a polymer with only two monomer units in it. So I'll form a dimer of my styrene. So if you look at this, here's one styrene unit, this is my radical initiator, and here's my second styrene unit. And again, I have another radical here, so it's ready to go again. So you draw the next addition to this molecule. So redraw the molecule that we have, the dimer, and you add a third styrene to it, and then check the result. All right, kind of running out of space here, but here's my trimer now. So if you want to, you can look again. Here's one styrene unit, here's a second styrene unit, here's a third styrene unit. Okay, so we're now making polystyrene. Now this is going to keep going until it runs into another one that has a radical on it, and let's look at that on the next slide with a termination step. So at some point in the reaction, two of these that are both radicals are going to come together, rather than having it be a chain reaction and reacting with a non-radical. So this is, of course, going to be a termination. All the rest of that was propagation steps. And at the termination step, that's what's going to give us our final polymer. So in this case, I have 3 monomer units in the first one, here, and 2 monomer units in the second one. So our polymer will have 5 repeating styrene units in it. That's an excessively small polymer. Usually they'll have hundreds or even thousands of groups, but we don't want to have to draw those. So So let's try and draw the product of this. So here's our polystyrene. Okay, made up with 5 monomer units. Now, if you think about it, if there's hundreds or thousands of monomer units that make it up, in the end, what's on the ends isn't going to affect the chemistry of the polystyrene very much. So if 99 or 999 out of 1,000 of them are this middle part, that's what's going to affect what the shape of polystyrene is like, what its properties are like. These little T-butoxy groups on the end are going to have very little effect, basically almost no effect, on the overall structure and function of the polystyrene in the end.